Hello everyone, my name is Christy Campbell. I'm a graduate in a pharmacy and biochemistry at the National University of San Marcos, and I'm presenting about a structure-based identification of potential Candida albicans malate synthase inhibitor from natural products of the South America biodiversity. The global incidence of candidemia has increased in the last time. Recent global estimates have suggested that 700,000 cases candidiasis occur annually. The higher proportion of Candida albicans is found in the North and Central Europe and the USA. 70% of the women report having had candidal vulvovaginitis at some point in their lifetimes. The most common responsible pathogen is Candida albicans in about 90% of the cases. The glyoxylate cycle is essential for the survival of many microorganisms, such as fungus. Malate synthase is the second key enzyme of the glyoxylate shunt, which converts glyoxylate into malate. Malate synthase genes share significant homology with proteins from fungi, plants, and bacteria, but certainly not mammals, which don't have the glyoxylate cycle. From the Library of Natural Components of Brazilian Biodiversity NUV, we will seek to identify new anti-malate synthase components and so to improve the availability of more extensive therapeutic arsenal against this opportunistic pathogen. The procedure performed are as follows. To identify new anti-malate synthase compounds, we first obtain ligand information from the NUV compound library, from which the SMILES will be converted into the required formats, PDB-KT, PDB, MOL2, and SDF. On the other hand, the malate synthase enzyme will be obtained using the AlphaFold program. Then both the ligands and the enzyme will be analyzed in docking programs such as BINA, LEDOC, AutoDock, and plants. The best score obtained from the enzyme ligand union will be chosen using the decision tree algorithm. This ligand will be analyzed for their pharmacokinetic properties, drug likeness, and medical chemistry friendliness of the best ligands in the Swiss ADME program. Finally, the best enzyme ligand complexes will be refined and optimized in the YSR structure program and then analyzed for molecular interaction in the post-view program. Figure 1 shows the correlation between the coupling results obtained with the BINA, plants, LEDOC, and AutoDock programs, where it observed that BINA has a higher correlation with the other programs analyzed. When analyzing the distribution of standardized docking scoring values, Z-score after docking procedures with the programs present in the figure 2, an overlap can be observed, which implies a correlation of the values found in the molecular modeling program. Figure 3 shows the heat map of standardized free energy of binding values, Z-score after docking procedures with using docking programs, the AutoDock, LEDOC, and BINA programs, considering the decision tree procedure for the selection of the best candidates for binding to malate synthase. On the absolute free energy heat map of binding values after docking procedures with AutoDock, LEDOC, and BINA programs, considering decision tree procedures for selection of the best candidates for the malate binding synthase that is observed in figure 4, show us that NUV 376, NUV 953, and NUV 1076 are the best candidates for binding with the enzyme. Table 2 shows the natural products with the best malate enzyme binding scores. These products follow Lipinski's rule of 5 without any violation, which make us assume that they have good solubility, absorption, and permeability. These 9 compounds are mostly aromatic derivatives, amino acid, peptides, alkaloids, and flavonoids. Here we can see the best ligands. And here we can see the best ligand bound to enzyme. This was done in the post-view program. The 9 analyzed natural compounds follow Lipinski's rule of 5 without any violation, which make us suppose that they present good solubility, absorption, and permeability. Therefore, these compounds are drugability candidates for the development of new antifungal against Candida albicans. Thank you.